In the last two episodes, we covered the detailed math of wave equations in general and Schrödinger's equation in particular. The main takeaway from those videos was that the electron wave function solutions for the hydrogen atom allowed by Schrödinger's equation can be enumerated with three quantum numbers, n, l, and m, which specify unique shapes of electron orbitals whose energy depends only on the principal quantum number n. In today's episode, we move beyond hydrogen and use those results to explain the structure of the periodic table and the basic chemical properties of the elements. Welcome to Atomic Universe. I'm Dan Bergstrom, material scientist. Before diving into using Schrödinger's equation to explain the periodic table, it will help to review what was already known about the periodic table prior to 1926. Soon after, Italian chemist Stanislaw Cannizzaro published a reasonably accurate list of elemental atomic weights in 1858. Chemists began to lay them out in order and noticed their chemical properties tended to repeat cyclically. Dmitry Mendeleev published what was recognized as the first periodic table in 1868, and he claimed in 1871 that the periodicity of the atomic properties when sorted by atomic weight implied that there were missing elements in the series. When gallium, scandium, and germanium were later discovered, they did indeed have the chemical properties that were predicted by Mendeleev's table. In 1911, Antonius van der Broek proposed that nuclear charge, not atomic weight, was the proper way to sort the elements, a hypothesis that was confirmed by spectroscopy data published by Henry Moseley in 1914. Moseley's spectroscopy work directly measured the nuclear charge of most of the known elements up to that of gold at atomic number 79, predicting new elements that were missing at atomic numbers 43, 61, and 75. In 1925, rhenium was confirmed to exist at atomic number 75, but it took more than 2 decades to discover technetium at 43 and promethium at 61, which have no stable isotopes. In 1913, a year before Moseley's predictions, Niels Bohr had modeled the atom based on the assumption the electron's angular momentum was quantized as an integral multiple of Planck's constant over 2 pi. This integer multiplier came to be called the principal quantum number n, and was the first step in explaining the structure of the periodic table. Bohr's model was that each row of the periodic table corresponded to one of his energy levels filling up. The n equals 1 row filled up after 2 electrons, and it took 8 electrons to fill in n equals 2 and n equals 3. The chemical properties of each element in this model depended only on the number of electrons in the outermost shell. Bohr, however, could not explain where the numbers 2 and 8 came from, and for n equals 4, his model based on octets didn't work very well. There was also another problem with the Bohr model found in the fine structure of light spectra emitted by atoms. Albert Michelson and Edward Morley, using the same interferometer they famously used to look for variations in the speed of light through ether, were able to collect atomic spectra with very high resolution, and showed in 1887 that many spectral lines were actually composed of doublets or triplets of closely spaced photon frequencies. Bohr's model for quantized angular momentum generated precisely quantized energies that he matched to photon frequencies in the observed spectra, but the doublets and triplets in the fine structure of the atomic spectra implied that not all electrons with the same principal quantum number had precisely the same energy. Focusing on this problem of small electron energy shifts that Bohr's model couldn't explain, German physicist Arnold Sommerfeld refined Bohr's model over the next several years to provide answers. Although Bohr's model assumed circular orbits, Sommerfeld suggested that elliptical orbits could still obey Bohr's quantization rules for angular momentum and energy levels. The principal quantum number n was still used to calculate the energy levels, but the angular momentum represented a second degree of freedom and was quantized with its own quantum number k. When k equaled n, then the orbit was a circle, but k could also be any integer less than n, describing an elliptical orbit with lower angular momentum but equivalent energy. Modern notation is to use L equal to k minus 1, and is quite often just called the angular momentum quantum number. Since k had to be less than or equal to n, L can take on any integer value from 0 to n minus 1. Having shown that there could be different orbits with the same quantum number n, Sommerfeld now used his model to explain how those orbits could have slightly different energy. In 1916, Sommerfeld published that since the electrons in the more eccentric orbits would be moving a significant fraction of the speed of light at their closest approach to the nucleus, the energy of orbits with different eccentricities would need different relativistic corrections to their orbital energy. His formula with this adjustment showed that these relativistic effects did indeed result in splitting the energy levels in a way that explained the fine structure of the atomic spectra. That same year, German physicist Friedrich Paschen, guided by Sommerfeld on exactly where to look, made precise measurements of the spectral lines of helium that exactly matched Sommerfeld's predictions. Even with this new quantum number, there were still anomalies in the spectral data that needed explaining. One of these was the Zeeman effect, discovered in 1896 by Dutch physicist Peter Zeeman. Zeeman collected atomic spectra from Bunsen burner flames and tested the effect of putting the flame in a strong magnetic field. He found that the magnetic field induced single spectral lines to split into multiple closely spaced lines. This effect suggested to Sommerfeld that energies of the orbiting electrons were shifted due to their interaction with the external magnetic field. Ampere's law says that an orbiting charge creates a magnetic moment perpendicular to the plane of the orbit, so the energy shift should depend on the cosine of the angle between this moment and the externally applied field. Now, if this angle were allowed to randomly take on any value, then on average there should be a broadening of the electron energies and a blurring of the resulting spectral lines, not the observed result of splitting into several distinct sharp lines. In 1920, Sommerfeld came up with a way to explain this by assuming that even the rotation of the angular momentum relative to an external magnetic field was quantized. Creating yet another quantum number, m, Sommerfeld quantized the component of the angular momentum in the direction of the magnetic field as m times the reduced Planck's constant. The magnetic moment of the orbiting electron was also quantized as a result, equaling m times the electron charge times the reduced Planck's constant divided by 2 times the electron mass. Thus, this new quantum number came to be called the magnetic quantum number and could take on any integral value from negative L to L. Viewers of my last episode on Schrödinger's equation will now recognize these same quantum numbers of n, L, and m emerged naturally from applying Schrödinger's equation to the potential of the hydrogen atom. The shapes of the hydrogen orbitals we calculated there were more complicated than Sommerfeld's ellipses. But if you think about it, the electron's de Broglie wave frequency is proportional to its momentum, so that means it's fair to think about a higher nodal frequency in the rotational direction as being related to the angular momentum. Since in Schrödinger's model, L represented the number of rotational vibration nodes, and m was the fraction of those nodes oriented about the z-axis, it makes perfect sense to think of L as the angular momentum quantum number and m as the fraction of the angular momentum aligned to a certain direction, in this case the magnetic field. So you see, these two models agree quite well. At this point, two curiosities came together for Australian physicist Wolfgang Pauli to explain with a new theory. The first was that if you add up the possibilities for unique combinations of the three quantum numbers, you get tantalizingly close to explaining the structure of the periodic table. The number of allowed permutations of quantum numbers increased as n squared, one solution for n equals 1, up to 16 solutions for n equals 4. But the number of elements per row in the actual periodic table was somehow always twice as big as a square number, 2, 8, 18, 32. The second curiosity was, although Sommerfeld's model was able to explain the Zeeman effect quite well in many cases, there were still unexplained cases like that sodium spectrum we saw earlier, where there's too much splitting of the lines to be explained by the possible combinations of angular momentum and magnetic quantum numbers. These unexplained cases became known as the anomalous Zeeman effect. In 1924, British physicist Edmund Stoner was able to show that these anomalous cases could be explained if the total angular momentum quantum number was modified to be L plus or minus 1/2. But it was not clear why these special cases should break the rule of integer quantum numbers that were obeyed the rest of the time. In 1925, Pauli's solution to both these problems had two parts. Firstly, he added a fourth quantum number that could take on plus or minus 1/2 the quantized angular momentum. The second was to declare if one electron had a certain set of four quantum numbers, any other electrons were excluded from having exactly the same numbers. For every distinct combination of n, L, and m quantum numbers, plus or minus 1/2 values were allowed for the new quantum number, so that two electrons could share the same NLM orbital, but no more. This is what we call today the Pauli exclusion principle. When an orbital did have two electrons, the plus and minus 1/2 factors in the angular momentum were opposite in sign, so canceled out. But when there was only one electron in an orbital, it could contribute to the total magnetic moment and create this anomalous Zeeman effect. And of course, with two electrons able to occupy each orbital, the periodic table rows of length 2 times n squared made perfect sense. Pauli initially referred to this new quantum number as a two-valued degree of freedom with an unknown physical interpretation. But before too long, Dutch physicists George Uhlenbeck and Samuel Goudsmit published their interpretation of this value as a spin of the electron, which is how we think of it today. Now, to be sure, if the electron were really spinning enough to give it an angular momentum equal to half of its orbital momentum, it would have to be spinning faster than the speed of light. But it is the case that when experiments have measured the amount of angular momentum intrinsic to electrons, it comes out as exactly equal to 1/2 the reduced Planck's constant. So the term spin is the best term we have to describe this quantum phenomenon. So now we have all the pieces in place to understand the structure of the periodic table. We have the solutions for the electron orbitals from the hydrogen atom as provided by Schrödinger's equation, quantized in n, l, and m. We have the concept of electron spin, quantized as m sub s, as plus or minus 1/2. And we have the Pauli exclusion principle stating that each electron in an atom needs its own unique set of these 4 quantum numbers. So let's start with the big picture. Here is a table of all the elements up to radon, where I've attempted to show all the orbitals with their accurate relative size. This is a little tricky since there are different ways of measuring atomic size experimentally, and I stop at radon because there are actually no agreed upon sizes for many of the heavier atoms. So this periodic table is incomplete, but the big picture is clear. As you move from left to right on the table, atoms are shrinking. This is because the positive charge of the nucleus increases with atomic number and the electrons are being pulled closer and closer to the center. If you look down the first column, however, you see a steady increase in radius. This is because the first element in each row is the first to populate a new energy level with a larger average radius in the radial distribution function. For instance, the largest atom in this table is cesium at atomic number 55. This is the atom whose electrons are first populated in the n equals 6 orbitals. All of cesium's other 54 electrons are inside that little pink sphere populated in the n equals 5 and lower energy levels. As you can imagine, that outermost electron of cesium doesn't feel the full pull of the 55 positively charged protons in the nucleus, because there's 54 other electrons getting in the way. In general, each atomic electron will modify the potential energy environment of all the others, scaling as n factorial and making calculating these interactions a nightmare. To make this plot, I've made estimations following an algorithm developed by American chemist John Slater in 1930. In his model, the effective nuclear charge attracted in an electron is reduced by repulsion from electrons with smaller or equal principal quantum number n. According to his rules, electrons at n-2 and lower levels are 100% effective at screening out nuclear charge, each electron canceling a proton's charge 1 for 1. Electrons at n-1 have a screening effectiveness between 85 and 100%. And electrons with the same quantum number n will have a screening effectiveness between 30% and 100%, all depending on the values of n and l. Note that instead of specifying the values for L, Slater used the chemist's convention of labeling the orbitals s, p, d, and f for L equals 0, 1, 2, and 3 respectively. For this plot, I've colored the s orbitals green, p orbitals purple, d orbitals blue, and the f orbitals yellow. The more transparent shades represent partially full orbitals and the more opaque ones are full. I've left the outermost s orbitals more transparent so you can see more of what's going on inside. So plotted this way, you can immediately see each column of the periodic table is grouping similar looking orbital clouds together. As we'll see when we go through the elements, the first 2 columns are populating the s orbitals, the last 6 are populating the p orbitals, and the middle 10 are populating the d orbitals, with the bottom row populating the f orbitals. The atomic symbols and numbers for each element have been color-coded to highlight these blocks of elements. As we go through the elements, I'll highlight 2 key energy values for each atom. The ionization energy, which is the energy needed to remove one electron from an element, and the electron affinity, which is the energy gained by adding an electron to an element. Since all chemical activity is just atoms exchanging electrons, knowing the energy for an atom to gain or lose an electron will tell you a lot about its chemical properties. As we will see, the value of these energies depends on the electron orbital configurations, and so the trends of these values will repeat along each row, giving similar atoms in each column similar chemical properties. So now let's examine our elements starting at the top. Hydrogen has an atomic number of 1, so 1 proton and 1 electron, and this electron will want to be at the lowest energy it can be, so it'll settle into the n equals 1, 1s orbital. The atomic radius of 0.53 angstroms is called the Bohr radius, and the ionization energy needed to pull its electron out of the atom will be 13.6 electron volts, the so-called Rydberg energy. The electron affinity for hydrogen is 0.75 electron volts. Now, it's reasonable to ask, why would a proton that has already attracted an electron into its orbit attract yet another one? I mean, the repulsive force of the electron already there will counteract the attractive force of the proton. Well, the answer is that the electron's charge is more smeared out compared to the proton's charge. Thinking about it classically, from the point of view of the second electron, the first electron has a 50% chance of being behind the proton at any given time, during which the second electron will see almost the full charge of the proton attracting it. At other times, the first electron will directly repel the second, but on average, there is a slight attraction. Moving on to helium with atomic number 2. Now both electrons can fit into the 1s orbital, but they have to have opposite spins. The 1s orbital is now full, and both electrons will feel the pull of the nucleus very strongly, pulling them into an atomic radius of only 0.3 angstroms, the smallest of any element. This full shell also screens the double positive charge of the nucleus very effectively, so the electron affinity drops to nothing. The ionization energy to pull one electron free has jumped to 24.6 electron volts, the largest of any element, but not quite double that of hydrogen. As the electron is pulled away from the center of the atom in the ionization process, the remaining electron will partially cancel the double positive charge of the nucleus, making the first electron relatively easier to remove. Still, it takes a lot of energy to ionize helium, making it very chemically inert, the first of our noble gases. With lithium at atomic number 3, there's no more room in the n equals 1 energy level, so the third electron needs to go to the n equals 2 level, where electrons have 4 times less binding energy. With this second energy level beginning to populate, we start a new row of the table, and the atomic radius takes a big jump up to 1.67 angstroms, more than 3 times the size of hydrogen. The ionization energy is also correspondingly lower at 5.39 eV, making lithium very chemically reactive, as anyone who has seen lithium dropped into a beaker of water can testify. With n equals 2, there are 2 choices for the value of the second quantum number L, either 0 or 1, representing the s and p orbitals respectively. The main difference between these 2 orbitals is their radial distribution function. Since these plots represent the probability of finding the electron, an electron in the 2s orbital is more likely to be found near the nucleus than one in the 2p orbital. Since the p orbital electrons are farther away on average, they see more cancellation of the nuclear charge by the 1s electrons, whereas the 2s electrons feel the pull of the nucleus more strongly. For this reason, 2s orbitals will have a lower energy and get filled by electrons before the 2p orbitals do. Lithium and beryllium will have 1 and 2 2s electrons respectively. With beryllium having a completely full 2s orbital, the electron affinity again drops to 0. As we move to boron at atomic number 5, the 2s orbital is now full, so the first 2p orbital starts to populate. You may ask which one, since the magnetic quantum number m can equal -1, 0, or 1. It turns out these are all equally likely, unless there's an externally applied magnetic field, in which case we define the z-axis to be parallel to that field, and the lowest energy will come from the m equals -1 shell. The electron's spin will also align to the magnetic field for lowest energy. Comparing to beryllium, the increased pull of the nucleus for boron has reduced the atomic radius from 1.12 to 0.87 angstroms. But the 2p orbital electrons are held to the atom slightly less strongly than the 2s electrons, so the ionization energy has dropped from 9.3 to 8.3 electron volts. As we move to carbon and nitrogen, the new electrons will want to populate their own p orbitals, spreading out due to the tendency of electrons to repel each other. The increased pull of the nucleus shrinks the atomic radii of carbon and nitrogen to 0.67 and 0.56 angstroms, respectively, a little bigger than hydrogen. Nitrogen has one electron in each of the three p orbitals, and this balance brings additional stability to the electron configuration, so the ionization energy has grown to 14.5 eV, but the electron affinity drops to a pretty low 0.07 eV. When we get to oxygen, the electrons have to start doubling up in the 2p orbitals, so the ionization energy drops to 13.6 eV and the electron affinity starts growing again. Fluorine's ionization energy increases again to 17.4 eV. These electrons are very hard to remove. Fluorine's electron affinity is also very high. Any electrons nearby, fluorine will capture with a binding energy of 3.4 electron volts, forming a negative ion whose electron configuration is similar to neon. The balanced nature of having 8 electrons filling all the s and p orbitals is very energetically favorable, so the highest electron affinities in the periodic table are found in fluorine's column, elements known as the halides, which are 1 proton short of being noble gases with full electron orbitals. In contrast, the electron affinity for neon is 0. Its n equals 2 shells are full, and there's no energy gain for an electron to be added to the n equals 3 energy level. High ionization energies and 0 electron affinities are what make the noble gases in this column chemically inert. Now we move to the n equals 3 row, which follows the same pattern as the n equals 2 row. The 3s orbitals will fill first for sodium and magnesium, and the next 6 atoms fill out the 3p orbitals until we have another noble gas with argon at atomic number 18. You can see why the chemical properties repeat with increasing atomic number. Within these 8 columns we've populated so far, the s and the p shells will always be the outermost electrons, which participate in the chemical reactions and are called the valence electrons. You'll often see these columns numbered 1 to 8 to represent the number of valence electrons for the atoms in that column. You will notice that the n equals 3 row does not include any elements with 3d electrons. With each increase in quantum number L, less of the electron's radial distribution function is near the nucleus. So electrons with larger L will be less attracted to the nucleus and have lower binding energy. In fact, the energy of the 3d orbital is so high, electrons will mostly prefer to populate the 4s orbitals first. So potassium and calcium at atomic numbers 19 and 20 do that, and we put them in columns 1 and 2 with other atoms that have 1 and 2 valence electrons. We don't see the 3d electrons start to populate until scandium at number 21. So we now start filling in the middle columns that we skipped over earlier with what are called the transition metals. Titanium and vanadium are 2 and then 3d shell electrons. But when we get to chromium, there's a shift. The 4s and 3d energy levels are close enough that when the crowding of 2 electrons in the 4s orbital can relieve itself by shifting one to the 3d orbitals, it does so. So for chromium, there is 1 electron in the 4s orbital and 1 in each of the 5 3d orbitals. From manganese through nickel, we go back to 2 electrons in the 4s state as the 3d orbitals begin to double populate, until we get to copper, where the d orbital plucks away 1 of the 4s electrons to give that complete d shell with 10 electrons. Having 1 or 2 electrons in their s orbitals, along with empty p orbitals, is what gives the metallic character to the transition metals. But the d orbital electrons do have secondary chemical effects. Because the 4s and 3d energy levels are so close, the exact balance between the number of s and d electrons for these transition metals can be easily shifted by the chemical environment, giving transition metals the flexibility to present a different effective valence number under different chemical conditions. The last of our transition metals in this row, zinc, tops off that empty 4s electron state from copper, and then afterwards gallium begins to fill the 4p orbitals as above. The full d shell electrons below are very stable, and they keep to themselves, so the 4s and 4p valence electrons in this p block will again dominate any chemical reactions. The 5th row of the periodic table largely mimics the 4th. The 5s orbitals fill first, then the 4d orbitals, and the 5p orbitals. One oddity in this row, however, is palladium at atomic number 46. Here, the atom prefers to have 10 electrons to make the 5d shells completely full, so it steals both electrons from the 5s shell, making it the only atom without any s shell valence electrons. As we populate the 6th row, we find that after the 6s orbitals are filled by cesium and barium, lanthanum puts an electron in the first 5d orbital, But with cerium, the 4f orbitals begin to populate and fill out what are called the lanthanide series of elements. Most times this is presented as its own row at the bottom of the periodic table. These 4f orbitals are buried deep under the n equals 6 and n equals 5 shells, so you won't see them in this plot. But this also means the f orbitals don't really participate in any chemical reactions. All of the lanthanides have 2 valence electrons in their 6s orbitals and have ionization energies around 6 electron volts with electron affinities around half an eV. This makes them all chemically similar and difficult to separate from each other, as they are frequently found mixed together in nature. The 5d orbital has 1 electron for cerium, gadolinium, and lutetium, but that electron gets pulled back into the 4f shell for the other lanthanides. After the f shells are full, we go back to filling out the 5d orbitals with the transition metals from hafnium through mercury, and finally the 6p orbitals fill up until we get to radon at atomic number 86. So to sum up, the periodic table structure is best thought of as being composed of blocks corresponding to the electron shells which are being populated as the atomic number of the elements is increased. Of course, in this plot I have been following the standard layout of the periodic tables which you'll see in chemistry books, a format which is directly descended from Mendeleev's original table before the nature of electron shells was really understood. The last thing I want to show you today is a much neater way to lay out the periodic table, one that's much more intuitive for understanding the underlying orbital quantum mechanics. This table was first proposed by French engineer Charles Genet in 1930 when he was 81 years old, and is known as the left-step periodic table. In this layout, the sequence of the orbital filling can be clearly understood from the relation of the principal quantum number n in relation to the row number. In the s columns, n equals the row number. In the p columns, n is the row number minus 1. In the d columns, n is the row number minus 2, and finally in the f columns, n is the row number minus 3. Within each row, the electrons will populate from the lowest value n orbitals first. So taking the 5th row as an example, the f block is empty because 5 minus 3 gives n equals 2, and there are no f orbitals possible for the n equals 2 energy level. The d block gives 5 minus 2, or n equals 3, so the 3d orbitals will populate first in this row, followed by the 4p orbitals, and finally the 5s orbitals. Although this layout makes the most sense from understanding the electron configurations of the elements, it does have the drawback of grouping helium with the alkaline earth metals like beryllium and magnesium. So I don't think they'll be rewriting the chemistry textbooks anytime soon, but if you ever need a quick cheat sheet for the electron configurations, now you know it exists. That's it for today's episode of Atomic Universe. Next up, we'll be looking at how these elements hook together by forming atomic bonds. Thanks for watching.